I'm from the University of Glasgow. I'm a reader there in responsive and interactive AI. I only recently joined there back in December. Before that, I was at City University of London, so quite a move to the north of the country. You can follow me on Twitter, Dr. Simone Stumpf. You can also send me emails if you have any follow-up questions. I'm quite happy to answer them. So what I'm going to talk about today is responsible AI and getting the human back into the loop, and some of my work that I've done relating to that, some of my current work, and then also looking ahead slightly to what I think the major challenges still are around getting the human back into the loop and doing something around responsible AI. Right, let's see. So in the abstract of this talk, I talked about the spring, summer, and autumn of AI, and some of you might be old enough to still remember the last AI winter, but it's really that we are in the spring times of AI right now. We have seen phenomenal increases in accuracy, particularly with the deep learning approaches, where some of these machine learning systems are much better in terms of accuracy than humans are. We are seeing much wider application areas of AI that are creeping more and more into mainstream applications. And we've also seen great advances in explainable AI, where I've also been working. So we are sort of on the uptrend at the moment. And I might want to remind you of the vision of explainable AI, where today, well, that was about nearly 10 years ago, where you had some machine learning system, and they were making some decisions or recommendations to the user, and then the user had this sort of headache of, well, why did you do that? Why not something else, and so on. They had certain questions, and the vision of explainable AI was really to develop these explainable models or explanation interfaces that could then explain to the user, and so they would understand why or why not, and why the decision was, why the system was making some decisions or some predictions. And it also coined this phrase of calibrated or appropriate trust. That meant that the user was not just relying blindly on a machine learning system, but it would also support this calibrated trust, so they were only relying on it when they should and not when they shouldn't. And there's been lots and lots of work going on since 2016, when DARPA launched the call for explainable AI. And so there's lots of work to make machine learning transparent or explainable. Obviously, at the easiest is sort of like, well, you just give the source code of the model, but that is really not what making machine learning transparent is all about. And so you have representations of the model or the model application, so where we might expose the model, i.e. given global explanation of how the model works, what data it uses, or as in the case of Lime, which I think everybody is hopefully familiar with, where you expose sort of a combination of features that contribute to a decision, and that is quite often called a local explanation. There's also lots of work to make explanations usable. So not only make the system explain itself, but how do we make the explanations so that they are usable by the user, by whoever is using the system. And there has been some great work around what should be explained. So should it be a global or local explanation? What are the intelligibility types? What should the content be of these explanations, coupled with work that looked at, well, how should we explain? So once we know what should be contained in these explanations, what's the best way of communicating this? Is it, for example, through natural language, through textual explanation, through visualizations, and so on? So there's been a great amount of work going on in that area, which is great. I'm coming from a slightly different perspective. So I prefer the term interpretability rather than explainability. And from my point of view, explainable or explainability is an ability of an AI system to explain itself. So it's very system-centric, right? It has nothing really to do with a user that you're explaining it to. And while these efforts are great, so for example, thinking about, well, how can you extract some explanations from, say, a deep learning system, which doesn't have any sort of ready-made explanations. What I'm more concerned about is this notion of interpretability. So this is really the human-centric ability of a user to build an appropriate mental model that guides interaction with the AI system. And that's also where this appropriate or calibrated trust comes in. And really that distinguishes the purpose of why we're doing all of this explaining. So it's related to a user, to whoever you're designing the system for. And that means that we have to build this appropriate mental model, and I'll say a little bit more about what mental models are in a minute. But this mental model guides the user to understand how the system works. They should be able to use the system successfully if they have an appropriate mental model, and they should also be able to troubleshoot the system and fix mistakes. Now, all of this work builds on mental models, which is not a new thing. They've been around for a good long while, since the early 80s or even before. And a mental model is really a kind of internal representation in someone's thought process for how something works in the real world. So it's kind of, a model. What we know of mental models is that users will build them, it's almost like an unstoppable force to guide how they interact, behave, or fix things when they go wrong. So how do you build mental models? I said, you can't really stop users building mental models, because that's what they do. They extend and adapt existing mental models in new circumstances. When they encounter, for example, new systems, they will draw on the mental models of similar systems that are around. If they don't have a appropriate mental model that they can extend or adapt, they will try and build a mental model of how things work by exploring these systems and using them and seeing what happens. You can also influence the building of mental models by teaching people how it works or having things explained. And that is where the connection between explainable AI and mental models comes in. So I said, great, you know, we are in this spring, but I think autumn might be on the horizon. So we know that while we have seen these increases in accuracy, AI still makes mistakes. And sometimes these mistakes are not that easy to spot, even though you know, you might want this calibrated trust. It should still be in high stakes system, for example. You know, they need to support the user rather than be applied automatically. And that has also meant that there have been certain calls by other researchers, but also in general, with the fear that AI is uncontrollable and violates users' autonomy, that you know they're just applying their logic and human decision making is sort of sidelined. And another strand of fears is really that AI just embeds and perpetuates these human biases and unfairness without being able to be controlled, without really knowing whether it does that and then being able to step in and correct that. So what I am proposing, and that is where a lot of my work has been focused on, is that I like to bring the human back into the loop, to really hope that we can enjoy this summer of AI. And what I think needs to happen is that we need to have explanations of how these machine learning systems work, to build an appropriate mental model, and also that has in effect the effect that users have calibrated trust. But then that allows hopefully the user, the human, to make appropriate changes at all stages of the process, to really get them back into the loop, to control what the machine learning system does and what it learns. So I'll briefly talk through a couple of experiments that we've been doing and that I've been involved with in the past. That is really in the area of explanatory debugging for interactive machine learning. So if you're not familiar with interactive machine learning, it's where there is a tight coupling between the system making predictions, the user providing feedback, and then that learning being integrated almost sort of, you know, as a sort of cycle, so a feedback and teaching cycle. What we've been doing is using that notion that we want the system to explain to the user how it makes decisions that will hopefully go along with a improved mental model that then allows the user to give some feedback or control the machine learning system, so it improves its behavior, and that obviously will also hopefully mean that the user is more satisfied with the system and you know, will continue using the system. We started working on that actually before 2009. I think some of our earlier publications were around 2007, from what I remember, and we're continuing in that vein. So let me show you a little bit what our earliest work was about to bring the human back into the loop. And what we did, we ran a very lo-fi experiment that was around email foldering. And what we did is we ran a machine learning system offline that classified different email messages into different folders. We just printed them out. If you notice, this is the email message, and then we provide an explanation underneath it. And because it was literally a paper prototype, we had people just mark them up with what they thought about it. It was a think aloud study as well, so we had quite rich data from which to draw on. And what we wanted to find out with this study was what explanation styles do end users prefer, and what do or can they feed back into the system. So that we explored 3 different explanation styles, which we called keyword, rule, and similarity. Keyword was, from what I can remember from all that while back, was just a naive Bayes, where we provided them the 5 words with the highest weight, and then also the 5 with the highest negative weight. Rule was a rule-based classification, where we just provided some kind of simple rules as output, and similarity was a nearest neighbor approach, where we just showed the message that was the most similar to that particular message, and that determined the folder that we predicted. What we found was that in general, and that has been sort of around and confirmed for quite a while now, is that people liked rule-based the best. So there was a general preference, or the most understanding in terms of rules, but we also found that people, our participants, really also got on well with keyword-based explanation approaches, but you have to watch out for negative weights. So when you talk about absence of features that determine a classification, that is really difficult for them to understand, and we have seen that in many other experiments that we held as well. Similarity-based explanations, or the similarity-based explanation style, had really serious understandability problems. So none of them really understood how it worked. However, that didn't determine the overall preference. That was very individual, and also based on the perceived accuracy of these explanations. When we flipped it around and asked them, so what should the machine learning system pay attention to improve the classification, 65% of participants made some feature adjustments. 12% talked around some different feature extraction or new features that the machine learning system wasn't paying attention to. And then because it was just a simple word-based, naive base. 5% also told us about some n-grams that they wanted to include. Fast forward about 5 years, give or take, we made quite some advances in our approach, and that's when we started to talk about explanatory debugging. And as part of that work, which we published at IUI in 2015, we investigated what principles should we apply for explanation in interactive machine learning. If we implement these principles in our approach, does this work better than existing approaches? So we came up with a few explanation and control principles. So an explanation should really be iterative. It should reveal itself and change over time. It should be sound. That means that it should be as faithful to the underlying machine learning algorithm as we can make it. It should be complete. So explain the entirety of what data is being used to make these predictions, but also it shouldn't overwhelm the user, which is a nice HCI principle to have. On the other side, in terms of control, we wanted to make these explanation actionable. So the user can actually interact and change something. So they are not just looking at explanations without being able to take some kind of action to feedback. They should be in this control, or the feedback should be incremental. So we are retraining, for example, the machine learning system after every kind of feedback. We make really small step incremental changes to the model. At the same time, any of that feedback should be reversible. So if something goes wrong, if the user notices that the changes that they're making is not going in the right direction, we have a way of reverting back to a previous state. So they can literally undo their changes. And then finally, we will honor the feedback. So even if it's bad feedback, we will do what they say. And we need to make sure that it's also perceived that we're making changes and honoring that feedback rather than just throwing it away. As part of that work, we came up with this interface called Lucidebug. It's actually available on GitHub as well, if you're ever interested in using it. It was really nice work by Todd Kolesa, who was a PhD student at the time, who is also a very gifted programmer. And also a really good user interface designer. So what we have here, this is the overview of the user interface. It looks like a mail reader, and we use 20 news groups as our data set, and we use 2 topics, which is baseball and hockey out of that. So that was the basis of our experiment. And what you see here is that we had various components and also various explanations. In this little pane, you see the headings of each of these messages. with a predicted topic, the prediction confidence in terms of percentages. We played around with different ways where you can visualize that as well. We have up arrows and down arrows. That means that since the last prediction, since the last change, the machine learning model has increased its confidence or decreased its confidence. We provide some overviews about how many messages have been filed away, how many are still unlabeled or untouched. We have a message pane, and you see here that several words are underlined, which are in the top 10 of the most important words or features that are used. We have a textual explanation, which I highlighted here to make it easier to read. And that is really part of the explanation, where this message has more important words about hockey than about baseball. So we showed them here. And the baseball folder has more messages than the hockey folder, and that yields a 67% probability that this message is about hockey. So we have some kind of explanation here about why this message was classified the way it was. And we also have another kind of explanation which shows the 10 highest words, or the 10 words with the highest weight appropriate to the classification. So that's baseball, Bill, Canadian, Dave, David, hockey player, players, and there were a few more down here. Now, the interesting thing is that the way that this work connects up to our earlier work was that we allowed users to change the feature weighting by simply dragging these bars up or down. So this explanation is interactive. And they can also highlight any of these words in this text message and add them as a new feature. So 2, maybe even 3 of the previous feedback requests that we had, we implemented in this prototype and could handle them. So what was the outcome of that? Well, it was really, really positive, I'm glad to say. So we had more accurate system accuracy with less effort. That meant that our accuracy was about 85% for our system versus 77% without explanation at the end of the study. So through getting these explanations, they were able to pin back appropriate changes that they could then make through the interface, and that yielded higher accuracy. And they were able to do that to making adjustments to 47 messages. But if they didn't have these explanations, they had to label or relabel 182 messages to make sort of improvements in accuracy. With the explanations, we were also able to improve their understanding, which is one of the points that we set out to do in the first place. And so we calculated a mental model score, so the higher the better, and that was on average 15.8, versus if they had no explanation, then it was about 10.4. Note that it's not 0. So people, just by using and exploring the system, were able to build some kind of mental model of how it worked, but it definitely wasn't as good as with the explanations. And also what we found was that the more participants understood how the system worked, the better they could make it. So higher accuracy increases were actually related to the mental model score. And when we measured workload measures, for example, mental demand through the NASA TLX survey, we also found that there was no difference between the group that used our system versus the group that didn't get these explanations. And if you remember, this is quite a complex interface, so we were quite pleased with that finding. So what do we know so far? Well, we can help users build better mental models by making information available of how the machine learning works. We also know that we can't just explain a decision. We also need to explain a little bit about how the system works in general. These better mental models help with spotting when a system goes wrong and use these systems better and also improve their accuracy. So where is this heading? In terms of human in the loop work and also bringing, sort of responsible AI development, what you need to consider is that you're working within a complex socio-technical system. So it's not just all about building better machine learning systems. It's actually how can we integrate these machine learning systems and also explanations into human use and human practices. And that means that any kind of explanations needs to bring in this socio-technical system. And in any socio-technical system, you have what the physical system is, what the task is, the structure or the organization in which people and the system and the task takes place. And also who are the people that use this as AI system. So we have to consider all of these, and all of these influence one another. You can't just separate one and just look at the physical system, for example, in isolation. You have to really look at this web of influence as you're building responsible AI systems. And just for explanations, you have to consider a variety of different aspects. So in terms of the physical system, you have to perhaps explain how it works, and that means explaining the models and the decisions. You have to build appropriate interfaces, and then you also have to decide on the interactions that a user is allowed to perhaps feedback or control the AI system. We also have to consider the task. So what does the machine learning system do? And one of the important distinctions is between high stake versus low stake. And that also influences when explanations might be required or are particularly useful. It also needs to take into account the level of automation that the machine learning or the AI system has, and the situational context in which it takes place. Is there time, for example, for detailed explanations, or do you need to provide explanations or provide input that that you know, where somebody has to make very quick decision making, for example. Over on the other side, the sort of more human side, is when we're talking about structure or the organization, we need to be mindful of why we want to explain something or what the purpose is of the AI system. So is it, for example, that we're explaining for increased adoption or trust or satisfaction? Do we explain so the user would be able to spot mistakes better or identify biases? Do we want them to have a better use or more appropriate trust, or do we want to explain so we can learn from users, like in this interactive machine learning examples that I've been showing you? And then finally, we really need to get to grips of who the user is and know their expectations and attitudes, what they're capable of doing. What is their ability to do, and also we need to really understand what are the existing mental models that we can leverage, and where do we want to shift the mental models to. So what is the target mental model? So all of this is really connected with the way that we design these systems, and again, that's where we need to bring people back into the loop. So how do you design for interpretability? And there have been various attempts at starting to do that. Essentially, though, nowadays, all explanations and systems are handcrafted for each user group and each application. I just wanted to call out, there's some really interesting work by IBAND that has been around, which is transparency design, which is essentially a modified user-centered design process to include users and experts to develop this target mental model, and then figuring out how to explain it. A more theory-driven way of designing has been proposed a few years ago by Wang et al. That aims to match people to explanation approaches and various ways of how that could work, and that's a really nice sort of higher level principled approach. And then I've recently adopted a co-design approach where I work with a small number of users to figure out how to explain something and then test it on a larger number of people. What I'm currently doing is really focusing more on bias and fairness, because I believe fairness and explainable AI go hand in hand. You can't really investigate whether an AI system is fair without knowing why and how it makes its decisions or predictions. More recently, I've been working on tools to find and mitigate bias or unfairness, and that is in vein of other work that has recently appeared, so FairSight and FairViz and all of these other approaches. But most of my work is really concerned with how do you bring not just humans in general back into the loop, but how can you involve lay users or domain experts to help you? Because most of these tools nowadays are still aimed at data scientists, as machine learning experts to run some statistical measures on the data to figure out, is it fair or not? And a lot of my work is thinking about, well, if there is fairness mitigation to be done, do we want to put that solely in the hands of data scientists? And my answer would be no, we need to involve more people, which then brings us on, well, how can we include stakeholders in that whole AI development process? Are there better ways than other? And also, once we integrate their suggestions, we need to still be aware that we don't just want to bake in biases from humans yet again. So how do we de-bias this human input that we're getting? And I put here, how do we de-bias humans? And that is probably a question for social scientists to answer, not computer scientists. So in terms of research challenges, I think where we're heading is that we do know that different people need different explanations, but we still have no clear idea what the distinguishing factors are between different people that need different explanations, and also how then to shape these explanations. So there's a lot of work still to go in that direction. There's also a real need to look at trust and reliance, and how can we support people to build this appropriate trust and reliance. And I believe that really is related to testing. So how can we encourage people to test these systems so they can figure out whether they work appropriately, or if there's any areas in that AI system that perhaps make systematic errors in the predictions. So there is that to do in terms of bringing people back into the loop. A lot of my work has been in interactive AI and making explanations interactive, but there are lots of other ways to allow people to provide feedback. And again, I think there's a lot of work still to be done to design these interactions that allow a human to feed back to the system in appropriate ways. And then finally, I think I already hinted in my last slide at that, is, well, how do we incorporate user feedback when we get it? How is a user able to control these systems? And again, there might be better or worse ways of doing that. And also in terms of fairness, how can we prevent bad feedback from entering the system and go into the training of the system? So I just wanted to leave a few minutes for questions. So really, I wanted to close with just a few key takeaways, which I think are really important in responsible AI and bringing humans back into the loop, which is that interpretability is fundamental. So it's not making a machine learning system explainable, although that is a part, but do not forget the purpose of why you're doing this, and the proof of the pudding is, do people actually understand it? And my second key takeaway is, well, you need to give humans the power to feedback and control. So we're moving much more from explanations, which is part of the responsible AI, just looking at them, nodding, and clicking OK, to, well, what is if I want to disagree with that, and feedback and control it. And that really brings me on to the final point, which is that we need to see these systems much more as a collaboration, as a team, so where humans and AI can work together to be more accurate, perhaps fairer, and also accountable. And with that, I think I'll close my presentation, and hopefully I'll have left enough time for questions.